Can you all see my screen?
Yep.
Okay, great. Well, in that case, I will wait for some more stragglers to filter in, and then I think we will start. Okay, I hear someone is very excited about our topic for today. Okay, so today we are beginning, well, we're continuing our discussion of how we can scale this notion of programming verification up to bigger and bigger programs. And over the last couple of weeks, we've covered one technique, which is called abstract interpretation. It's this idea that we can sort of take the we can take this verification that we're doing and boil it down to some rules that we apply specifically to individual functions for some finite set of conditions. So we talked about this idea of having a fixed set of conditions that describe program variables and states and how we're going to merge them and then transfer those states across function calls. We talked about how to deal with control flow using refinement functions in one of these analyses. And we talked about some interesting types of conditions like this octagon domain that we discussed. Okay, so that was all good. That was our way of defining, in effect, simplified program verification approach where there's fewer things we can state. Our language of specification is simplified, and that allows us to scale up the analysis because it's a big program, but we only learn simple things about it, so the analysis itself is relatively quick. Today, we're switching from abstract interpretation, that technique where we have simplified things that we can say about programs, so we can say about larger programs, to dependent types. And in some sense, you can say that dependent types take the opposite approach. They provide as rich as possible a language to state facts about your programs in, so that you can write shorter programs that you can verify in a simple way. And so that's another form of scalability. Scalability not by simplifying the analysis to scale to big programs, but by simplifying the programs in some sense to scale to the analysis available. And so we'll be covering this topic over a couple of lectures. Today we'll talk about this overall sort of idea behind this, which is a philosophy called propositions as types. And then we'll look at two concrete things that we add to our programming language to make this possible, namely inductive types. That's going to be our next lecture. We'll talk a little bit about computation, and type dependency. That's where we'll talk a little bit about the notion of types that depend on values. But I'm going to start today by talking about this, I called it a philosophy of propositions as types. And what I really mean by that is we're going to discuss a formal language in which you can write down proofs of various theorems. And this formal language is going to be built out of what are called introduction and elimination rules. And I'll discuss that in just a little bit. And then what we're going to look at is how we can mix programs that compute values with programs that develop proofs. We're going to take our formal language for writing down proofs and try to mix it with our language for writing down programs. And the goal of this is ultimately we'll find that if we do this mixture, we find that proofs take the form or play the part of programs with the propositions they're proving playing the part of types. And so in a sense, we'll find that type theory, the type theory being the process of assigning a type to a program, plays the role of proof checking, taking a proof and determining what proposition it proves, if any. So what I sort of hope that you discover over the course of this lecture is that everything that we've been learning, in the first half of the class, we learned about proofs and how to automatically find them. Then the second half of the class, we learned about programs and how we can tie them to proofs. Hopefully at the end of this series of lectures, you'll discover that actually we were talking about one and the same thing in both halves. Proofs and programs kind of the same thing, and there's deep interrelationships between them. I think mathematically, this is probably the deepest and sort of most, what's another good word for deep that isn't deep, man? It's just a very mathematically interesting idea that has connections to all kinds of interesting other mathematical things. But I think it's also something of compelling practical interest. So after we have our 3 lectures on dependent types, we're going to look at one application of dependent types, which is a project out of MIT by Adam Chapala using dependent type theory to both write down a set of cryptographic functions, cryptographic primitives called elliptic curves primitives, and also mix that program with a proof that the program is correct, and automatically write basically one relatively simple program that can automatically generate C code for different architectures optimized for that architecture to do these cryptographic primitives. So even if this seems initially like it's a little mathematically abstract, we're going to close the loop back on this. We're going to start this lecture with logic and that question of how do you write down a proof. But as we go through these couple of lectures, we're going to close the loop and tie that back to writing down short programs that you can prove interesting facts about, and then mix computation with proofs to generate efficient verified implementations. So that's kind of the broad vision of this section of the class. This is the last section of the class, so buckle in. There's only one more. And let's start by talking about the question of what exactly, let's just get back to the third lecture of the class. What exactly are proofs? How exactly do they work? But before that, let me take any questions on this general idea. I know that some of you have heard of dependent types or propositions as types before, and maybe you wanted to clarify what you've heard against what I just said about it. And as usual, I'll take questions using the raise hand button in the participants window in Zoom. Go ahead, Calvin.
So I don't want to go too off topic here, but I remember hearing about how these dependent type theories are like constructivist logics, and I wonder if that is like related to like how the program is like the construction of the proof, or.
I'll be honest. This is like sort of a this is a little bit of a tangent, but let me answer it quickly. Constructivist is a term for a philosophy of mathematics that was probably previously popular in like 1910. What it actually means is a little complicated. It is maybe related to the double negation elimination rule. I don't think it's actually that important for discussing dependent type theory. You can write down dependent type theories that are classic or constructivist. And I think we basically found the distinction doesn't matter that much in practice. There are, still people who think that, non-constructive proofs in math are like, not legitimate, but there's also people who think that, for example, proof by brute force search is illegitimate. I remember, 20 or 30 years ago, when the four-color theorem was proved, which was initially proved by writing a computer program to look at 1,400 different cases that come up. Some mathematicians felt that that was, not a legitimate proof, but I don't think anyone really rejects I don't think mathematicians these days actually reject that idea. It turns out mathematicians have caught up to the idea that we have computers now. So I think the constructivist or not is, I'm sure there are people out there who disagree. I know some of them, but in some sense, this is kind of orthogonal to the question of dependent type theory, which is really just this idea we're going to write down a formal language in which we can write down proofs. Any other questions broadly about, anything you may have heard about dependent type theory and want clarified now? All right, in that case, let's get into it. And let's start with this question of how do you write down what's a proof? And you'll recall early in the class, we had these like horizontal line things. They came up a lot in this that first section of the class that people didn't like. But to jog your memory a little bit, with what we'd have in this case is we'd have a horizontal line, and the stuff above that line, like the stuff over here, that was like an assumption, or like if that was true, then the stuff below the line was true. So we use these to write down. So, for example, here, rules for how you reason about for alls. So we said that if you want to prove something that's a for all, you have to prove the thing inside the for all given with just some extra new variable x, and we know that the fact that that's a new variable is expressed over here. So just jogging your memory about these things. Broadly speaking, those things are what we call inference rules or proof rules. And the way they work is they say, well, if you want to prove the thing below the line, you need to prove first the thing above the line. If you can prove the thing above the line, or if you assume the thing above the line, then you can derive the thing below the line. And I just wrote two different sentences describing what it means, but really these are the same idea, right? If the thing above the line is true, then the thing below the line is true, and vice versa. So in the beginning of the class, because I kind of wanted to just give you a brief overview of what we meant by first order logic, I focused on inference rules for things like for all and there exists, the ones you see on this slide. But let's try to simplify this a little bit and look at the proof rules for something like and. So how do you prove that A and B is true? Well, if you want to prove that A and B is true, it seems like it would be sufficient to prove that A is true and then also prove that B is true. And so when we have multiple things to do, we put both of them above the line. So what this proof rule is saying is, if you want to prove that A and B is true, then all you need to prove is that A is true, and then separately prove that B is true. And so similarly, if you want to prove or, well, you don't need to prove that A is true and B is true to prove or. It's actually sufficient to just prove A. If you've proven A, you know that A or B is true. And well, of course, if you've proven B, that's also enough to prove that A or B is true. So you've got these proof rules. And in these rules, the ones I've written down, we've always got the thing that we want to prove, like an and at the bottom. And then the stuff above, you see, tends to take the form of arbitrary variables. So these are proof rules for and or. But let me write one down for implication as well, because implication is sort of an interesting thing that happens. And with implication, we first need to introduce this idea of hypothetical reasoning. We do this all the time in mathematics or computer science. We talk about variables. We say, suppose x is a positive integer. Suppose we have some tree t. So when we talk about hypothetical reasoning, we usually introduce this extra thing to our proof rules. So we've got this weird symbol called a turnstile, I guess because it looks like the thing you pass when you get on the subway. We don't really have that, but in New York where I grew up, we did. So we introduced this turnstile, and then to the left of the turnstile, we have this big weird thing that's called a gamma. And that gamma is what we call a context. It contains all of the assumptions that you've made. So when we say let x be a positive integer, gamma would be x is a positive integer. And then the thing on the right-hand side of the turnstile is whatever came after the then in your sentence. So implications, well, naturally implications are related to hypothetical reasoning, because implications are all about if something were true, then something else would be true. And so the rule we have is that if you want to prove an implication, A implies B, it's enough to prove B assuming A. So what you've got going on here is you've got the assumption added into the context. So the hypothesis A in A implies B that turned into an assumption that you're allowed to use to prove B. So hopefully, well, let me take questions on so far, and or and proof rules. Hopefully this is jogging your memory a little bit of stuff we did toward the beginning of class. But if you've forgotten some of it, now is a great time to ask. And I'm sure many of you are sitting there trying to jog your memories, so feel free to ask. Go ahead, Skylar.
So the turnstile basically means that given that the thing before the turnstile is true, then the thing after the turnstile is true?
Yes.
Okay.
And so if you really wanted to, you could read this top thing here as something like, gamma and A implies B, that's above the line. And below the line, you've got like gamma implies A implies B. So if you want to think of that as just an implication, you can. There is a reason we keep those two separate, but the reason is kind of weird and complicated and not that important. It's about the difference between the language and the meta language. But you can think of that as, yeah, you can read that turnstile directly as an implication. You can read it as if the thing to the left of the turnstile is true, then the thing to the right of the turnstile is true. And luckily the turnstile looks a little bit like an arrow. Other questions? Okay, cool. So far, you've seen that the proof rules that we have written down are, generally speaking, of the kind that below the line of the proof rule, like down here, you've got the particular logical operator you're talking about, like implication. And then above the line, you tend to have just these, just these bare variables in various contexts. And so far, those, so far what we've written down in these assumptions are things like just logical propositions, but we could add also variable bindings to those. So for example, here we have the question of how might you prove that for all integers x, some proposition p is true of x. And to prove that, I say it's enough to prove p of x under the assumption only that x is an integer. Right? It makes sense. If you want to prove something for all integers, x, then you know that x is an integer, but you don't know anything else. And so again, what we've done is we have the logical operator that we want to prove below the line here. And we've taken, and then above the line, we have that same P of X, and we've added an assumption. So what we've got here, we've got, you can read this assumption as, X is actually an integer, or you could treat it as a variable binding. You can think of X as pre-existing and this as basically a fact about X. X is an integer, or you can think of this as introducing a new variable X. And by the way, if you squint at this for all rule, you'll notice that it looks a lot like the rule for implication that we just covered. And it makes sense. They both involve some kind of hypothetical reasoning. Hypotheses that X is an integer, or hypotheses that some proposition is true. So you can see here that the rule looks very similar, except in one case we have an A, and in another case we have X colon int, and otherwise they play basically the same role. So in each of these cases, we've written down rules that allow us to prove a certain logical connective. So that connective, that operator, goes below the line. And that's because so far what we've done. Oh, my apologies. Yes, I did want to note this. So what I've done so far is what I've done here is I've allowed you to write, variable comes from some type or some set to the left of the turnstile as an assumption. And that kind of makes sense. So if we can ask, if A and B are integers, well, then A plus B is also an integer. But if they're floats, A plus B is a float, right? And if you think about this, this could be like a generic function in, Java or C++, or if it's Python, you can think of this as operator overloading going on. So what we've got going on here is that if you want to, so similarly, if you want to prove something that's like an existential, so you want to prove that there exists an X that satisfies some property, then it's enough to prove that that's satisfied for some expression E, for some value, where E represents that value. And of course, we need to have that E itself is an integer in this case. It's some expression representing an integer. So we've got this this idea now that these variable bindings themselves, like B is an integer, E is an integer, they're also facts that we might have interest in talking about. We might be interested in knowing that some value is an integer, or it's a float, or it's a string, or something else. So I'm just trying to introduce that into the kind of propositions that can appear to the left and right of the arrow. Okay, so that's for how to prove various statements below the line. But there's another kind of rule that we're interested in, which is what about rules where we want to handle assumptions? So instead of having the logical connective that we want below the line and trying to figure out what we need in order to prove it, we're going to want to go backwards. Instead of going from top down, we kind of want to know, how do I derive a certain fact given specific assumptions? Because again, reasoning from assumptions is something we're doing all the time in logic. So the kind of rules on the left where we figure out how to prove a certain thing, given what do we need to prove a certain thing, those are called introduction rules. And they're opposite, where we ask, given certain assumptions, what can I prove? Those are called elimination rules. So far we've looked at a bunch of elimination rules, rules like here where you have the logical connective below the line, we're introducing an existential. Well, now I want to look at the opposite, where we talk about how do we eliminate certain operations, how do we use certain assumptions. So for example, for and, we've already looked at the introduction rule. We said that if you want to prove A and B, it's sufficient to prove A and to prove B. But what if you're given A and B as an assumption? Well, if you know A and B, you certainly know A. So given, if you're allowed to assume that A and B is true, you certainly know that A is true. And likewise, you know that B is true. So you can see that here, the introduction and the elimination rules, well, in fact, the elimination and introduction rules are basically opposites, right? The introduction rules allow us to take an A and a B and put them together into an A and B. The elimination rules allow us to take an A and B and take out the A, take out the B. The fact that these are opposites makes sense. Basically, we're saying you can't, get like free information by taking an A and a B, proving A and B from them, then using that proof, learn A and B separately. You shouldn't be able to get new information that way. So I won't go that more into this idea of no free information this time, but we'll talk about that next time when we talk about computation. Let's get back to this idea of elimination rules. So recall, elimination rules have the logical operator we're interested above the line. And then they ask, given that this is above the line, what can we prove? So here we looked at and. What about implication? If we know that A implies B, what can we do with that? Well, certainly if we know that A implies B and we also know A, we should be able to learn B. And so this is the elimination rule for implication. You'll often hear this called modus ponens because I guess like back in the 1500s, we all spoke Latin. I don't even know what modus ponens means actually, and I took Latin, which is embarrassing. So we have we have this elimination rule. This elimination rule has the implication above the line as an assumption. It tells us what we can do with that assumption, how we can derive some new fact from that assumption. And similarly, we could look at the elimination rule for or. You might call this elimination rule case analysis. It says, if we know that A or B is the case, how do we learn some other fact C? Well, you'll need to be able to derive C from A. You'll need to be able to derive C from B, because you don't know which of A and B is true. And you need to prove C in either case. But if you know that A or B is true, if A implies C and if B implies C, then A or B should also imply C. And so that's what this elimination rule is doing. So again, just to get at these. Thank you, Skylar. I don't think your translation helped that much. This was in the chat. Anyway, sorry. So what we've got here, again, we've got elimination rules that start with a logical connective as an assumption, allow you to derive some other fact. And then we've also looked at introduction rules where we start with some facts and we are able to prove some logical operation. These are two basically opposites. They work together. There's some sensible rules for how they should interrelate. So questions about introduction and elimination rules. Go ahead, Skylar.
Why are they called elimination rules? What's being eliminated?
Yeah, that's a great question. Fantastic question. So introduction rule makes sense because we didn't have an and now we do. We've introduced an and into the equation. And I guess kind of the idea is like you had an and you don't have one anymore. So like you've eliminated the and. I don't know. I don't really like introduction and elimination that much, but they're the terminology we use. It doesn't really make sense, right? Because like if you knew that A and B is true, you still know it. Like even if you also go ahead and learn A from it. Notes on some structural logics notwithstanding. So yeah, I don't really know why they're called elimination. I don't think it makes that much sense, but they're vaguely opposite sounding words. It's good enough. We computer scientists are not great with names. Calvin, question?
So is like A space B like A and B in the meta logic, as opposed to like A and B with the like wedge?
Yeah, yes. And if you didn't follow that question, that's okay. I'm trying to, in this class, basically elide the difference between the language and the meta language, or the logic and the meta logic. This is a thing that will come up, in an advanced math class, but it's not that important to just, understanding the basics of how this stuff works. But yes, yeah, you could imagine that the A with the spaces and then the B, that's kind of like an and. And if you read it that way, that's fine. Other questions? Okay, great. Well, in that case, we've seen some examples of introduction rules. We've seen some examples of elimination rules. So now I have a little exercise for all of you. So the exercise is write down some introduction and elimination rules for negation. And it might be helpful in this case to remember that negation, not P, you can think of that as implies false. So you'll need to think a little bit about how false would work, but just write down rules. What do you need to be able to prove that not P? And also, what do you, if you know that not P, what should you be able to learn? So let's take a minute to write down an elimination and an introduction rule. Okay, hopefully you have scratched out something that looks like an introduction and elimination rule. I'm going to try something like weird and different. I'm going to attempt to use the Zoom breakout rooms feature. So I don't know what'll happen, but I think you're about to be randomly paired off in groups of a couple. And so compare with whoever you're paired with and discuss to see if you feel like you've made any, you've written down the introduction and elimination rules correctly. So let's see how this works. Okay, so I think you are now all in various rooms. You probably have a thing that you need to click to join the breakout room. And feel free to unmute yourselves and talk.
I got paired out with Galaxy Note 8.
Yeah, to be honest, I don't really know what the deal is with Galaxy Note 8. I find it kind of weird. I've moved you.
Oh. But now I don't have the option to join the breakout room because, oh, I see.
I'm sorry. Listen, we're gonna, okay. You guys are done?
Yes.
Yeah,
Okay.
it seems to work pretty well.
Yeah.
It's a whole big experiment.
Okay,
Learning.
so we were supposed to leave the breakout room.
It's fine. Yeah, you can hang out here. I'll probably call off the breakout rooms in another moment or so. Yeah, I'm gonna do that.
Do you have
There's a countdown.
so
I
so
can't
you have a
close
button that
immediately. It takes
cancels
a minute.
the breakout rooms?
Sorry?
You have a button that just cancels the breakout rooms?
I clicked it and it said they'll close in a minute. All right, are you all back? Is that how this works? Is everyone back here?
I'm back here.
I think so. I think so. You all look back. Okay. Well, this was an interesting technological experiment. I hope you all had fun. Who feels like they have something that might be an introduction or elimination rule? Feel free to click the hand. Go ahead, Scott.
I have no idea if this is right, but that hasn't stopped me before.
Perfect. That's the right attitude. You learn
So
more.
I put P implies false on the top and then not P on the bottom for the introduction rule. And then for the elimination rule, I just swapped them.
Okay. This is definitely a valid way to go. So you're saying like, look, if you know not P, then you really know P implies false, and vice versa. Like, you know. Okay, that's pretty legitimate. Now we can expand this going one step further. We can say we actually know how to make a P implies false as well. Right? So not only do we know how to make a not P, we can actually go back one step. We can say, well, we know how to make a P implies false. So anyone want to try to fill in that one step further? So who remembers the rule for introducing implications? I mean, we've got an implication here below the line that we want to somehow introduce by writing stuff above the line. Okay, so if you remember, implication involves reasoning about hypotheticals. So when we say that not P is to introduce not P, we need to prove that P implies false. That means we need to know that assuming P, false is true. So if we add our little context here on the left of our facts, we know that to prove an implication, we take the hypothesis, we make it into an assumption. So we can unfold this one step further just using our definition of implication, and we get this introduction rule. We have, and the way you read this is to say, to prove that not P is true, you need to assume P and prove false. So questions on that? Anyone have something
quick
like
question.
this? Oh yeah, go ahead.
Do we treat P as maybe a Boolean or an entire proof? I guess I'm asking what P is.
Yeah, P is some proposition. So like
Okay.
like pigs fly. Right. So, you know, we're saying to prove that pigs do not fly, first assume that pigs fly, and then derive some obvious falsehood, like you know, we would not be as good at eating bacon in that case.
Gotcha. Thank you.
Other questions? Okay, so what about our elimination rules? Skylar did a great job here writing out, you know, first of all, if you have a negation, that's really P implies false. So we can actually take that one step further. We can recall our rule for using, aka eliminating, implications. So who remembers the rule for using implications? You know, I shouldn't ask these who remembers questions. I think they're a bad question. So I'll just continue trucking, honestly. So remember a rule for using implications. Well, the implication means if P is true, then false is true. So to use that, we naturally need to know that P is true as well. And so if we know that P is true and we know that not P is true, then we derive a falsehood. And in fact, y'all remember that if you assume false, we treat conventionally that if you assume false, you can prove anything at all. So you can almost write this like this. If you know that not P is true and you know that P is true, if both of those are assumptions, that's an obvious contradiction, and the result can only be that anything at all is true. So that's why I write a Q below the line. So these might be some ways that you write introduction elimination rules. You could go the sort of light approach, just write down definitionally, it's the same. You can turn it in and out of an implication, or we can unfold that one step further and we could say above the line here, we have assume P is true, prove false to prove not P. And conversely, if you know that P is false, well, and you also know that P is true, you can learn anything else. And to answer the question in the chat, the gamma again is the list of things we're assuming to be true. It's our list of assumptions. So when I write gamma comma P in the top left corner over here, what I mean is like the list that is all the things in gamma and then also P tacked on to the end. Any other questions? Yeah, gamma is everything that we're assuming. I'm not sure about the last question in the chat, but if you ask it in audio, maybe you can explain yourself. Oh, I see. You're asking how to pronounce it. Yeah, the thing that I'm using for false, this like upside down T, I call it false. Y'all can call it whatever. Okay. Okay, so just to rewind with what we've covered so far. What we've covered so far is this idea of rules for how we can prove or make use of assumptions that take the form of the various logical operators. How do we prove an and? How do we prove an or an implication? And also, how do we make use of assumptions that take the form of an and or an or or an implication? So now that we have these basic proof rules in mind, which are kind of like the individual moves of a game, we can talk about the sort of overall goal of the game, which is, our goal is to take these individual proof steps and combine them together into a big proof. So a valid proof, that's just a series of proof rules that you've applied one after another, kind of like some of my scribblings in that last exercise. And if we want to write down proofs for other people to read, it would be convenient to record which rules we used when. So for example, here was our rule for implication. Just to review that, it's saying that if we want to prove an implication, A implies B, then we get to assume A, and then we need to prove B as a consequence. So what would it take to write down our use there of that proof rule? Well, we'd need to record that we use the proof rule for introducing implication. There might be, other things that we could be introducing at the same time. We could, introduce an and instead. Then we'd need to record which assumption we want to apply here. So, you write down that you're assuming A. And then finally, you'd want to record your proof of B. You'd need to write down that whatever it is, whatever reasoning you use to prove B assuming A, you need to write that down as well. So that together would make for a proof of A implies B. So what we've done so far is we've just talked about these things like, oh, now I write down this, now I write down that, I assume that, etc. But I'd like to make this a little more formal and introduce some kind of concise formal language for writing down which proof rules I used when. So let's do that. The first goal is we have to write down the proof rule that we used. And so I'm going to write that down. It's introducing an implication. So I'm going to call it II. So I'm just going to write an II there to the left of that A implies B. That's just going to be the proof that I use to prove A implies B. Now that records the proof rule. Next, I want to record my proof of B. So, I don't know what exactly your proof of B is. Obviously, it'll depend on what B is, it can be any kind of thing. But let's assume you have some kind of proof. And let's write down E just to represent that whole proof, whatever it is. So now I want to write down not just that I'm introducing an implication, that's the II, but I also want to write down my proof of B. So it's introducing an implication, and it's using E to prove the consequent B. And then I also need to record my assumption, record in between these parentheses that I'm actually using, A as the assumption of my implication. So let me just add that. I'm going to give that assumption a name, X. So I'm going to write down II, X is a proof of A. And then from that, I have E, which is my proof. So what we've done here, basically, before, in any of these terms, below the line, in the gamma, to the right of the turnstile, anywhere at all, we would just have a single proposition written down. And now for each proposition, on the left of it, I have a little thingy written down which represents my proof of that. So what this is saying is that if I can write down a proof E of B, and in that proof, I'm allowed to assume that there's some kind of proof X of A. Well, in that case, this term here, II of X colon A comma E, that is going to represent my proof of A implies B. And again, there's nothing special about II, I just made it up right now, right? It's just a little bit of syntax to record all of the pieces that I need to use this proof rule appropriately. Write down the assumption, my proof of the consequent, I have a name for introducing implication, that's why it's called II. So questions right now about this idea that we're writing down little pieces. You can think of them as code, or you can think of them as a shorthand, just a little shorthand for remembering which proof rules we used when. Questions about this idea? Yeah, go ahead, Skylar.
So if we're thinking of proofs as programs, would it be fair to think of these as functions?
You can think of this as like II as like a function. Those kind of weird. It's not like, what is X colon A? Like I would think of this as just like a concise formal language. You can think of it as a programming language or like a configuration language, right? Something you can type into the computer that would represent the actual steps that you did. So the way this would work, right, is like, suppose what I'm actually proving is like A implies, suppose what I actually want to prove is A implies B and C. So I've got my implication here of B and C. And then I'm going to have some proof over here, I guess, of B and of C. And, you know, there's so this term E itself is going to contain some additional, like it's going to discuss how I proved B and how I proved C and so on. So it's really going to look like kind of like a big, you know, maybe like a big program or just like a big sort of, you know, almost like a config file, right? That describes all the proof rules I've applied one after another. I mean, you're right that eventually I'll turn around and tell you that these things are like programs. But I don't think you need to like try to shoehorn it into that box right now. You know, this is just a piece of syntax that we're inventing to write down how we use proof rules. Does that answer your question? Is that like, does that make sense?
Yeah, that works. Thanks.
Okay. Any other questions? Okay, then I'm just going to make one sort of final change. I introduced the syntax with the II, etc. I'm going to replace one like totally inscrutable abbreviation II with a different one. So I'm just going to change the syntax a little bit and just replace that II with a lambda. And this hopefully will look just like compellingly similar to a program now. So now what I've got is I'm still writing down the same stuff. It's just a piece of notation to describe the proof rules I use. Here I've written down the assumption I used. Here I wrote down my proof of the consequent. The little lambda just replaces II for describing the proof rule I used. Lambda, for whatever reason, stands for introduce an implication. So that's the little bit of notation we've invented for writing down this particular proof rule. And we can introduce other proof rules, right? So here's the proof rule for using implications. Remember that to use an implication, if we know that A implies B and we know A, we should be able to learn B. And all I've done here is I've given a name to my proof of A implies B and a name to my proof of A. And then I've invented a new little piece of syntax, which is going to look a lot like function application. But it's just a piece of syntax, really, for using this proof of A implies B and together with my proof of A to gain a proof of B. So I'm picking the notation now to be kind of suggestive, but you know, it's suggestive notation, but it's really only there as a notation for writing down proofs. So questions about this idea of you know, notations for proofs and how I've introduced notations for introduction and for elimination rules. You'll note that the common pattern is that above the line, there are lots of bare variables, and below the line, there's new syntax. And that makes sense because you get the stuff below the line by applying the proof rule. Questions? Okay. Well, here there's this there's like a little bit of weirdness here to the way I've written this down, because what I've written up here, it's kind of hard to tell. Did I mean that X is a proof of A, or did I mean that X is a variable of type A? You know, because remember we had this notation that like, you know, X is an integer, could be to the left of the line. So that's a little bit of confusion that can come up when using notation like this. But luckily, it turns out that confusion isn't really that harmful because really you can think of this form where X is a variable of type A and B is some property that might be about X. you can think of that still as being introduced by the same lambda term. In some sense, the only difference between implication, which we see here, and quantification, which we see here, is that in implication, you don't expect B to mention X. You know, you don't expect your proof to be discussing the proof of some unrelated fact. And in this case, you do expect B to be mentioning X because you expect B to be some property about X, the variable. But it turns out, you know, it turns out not to be that confusing to just use this distinction of uses X or not as the main differentiator between these. So we'll just keep the same piece of syntax, the lambda and the function application, both for quantification, namely for all, and for implication. With just the caveat that you think of these B's as having things substituted into them, or you don't. So that's given us notation to write down. You can think of it as 4 proof rules: introduction and elimination, for implication, and for all, universal quantification. What about some other terms? What about and terms? Well, we've seen already how you prove and terms. So for and terms, we said that if you know that A is true and you know that B is true, you know that A and B is true. And the notation I'm going to choose for representing that, it's going to say if we have a proof of A and a proof of B, I'm going to put those 2 proofs between a pair of parentheses. And that's going to represent the proof rule and introduction, that pair of parentheses. And similarly for eliminating and terms, well, I'm going to have some proof of A and B. I'm going to use first and second to represent the 2 things I can derive out of A and B, my proof of A and my proof of B. So again, this is just coming up with notation for writing down proofs. I've basically picked up one piece of notation for every rule that I've written down for proofs. And if you want, you can think of this as proofs of and being a kind of a structure with 2 elements, like a C structure, like a pair, or like a Python tuple, right? It's a structure that contains a proof of P1, a proof of A, and a proof P2 of B. And so naturally, if I have those 2 proofs, I can put them together in a structure. If I have this structure, I can extract the proof of A and the proof of B out of it. So questions about proof rules for and introduction and elimination. Okay, then if this makes sense for and terms, let's also look at or terms, which kind of the natural sort of dual to and terms. Actually, let's look at the introduction rules first. So my introduction rules were that if I know A is true, or if I know B is true, either of those is sufficient to derive A or B. And so just to write down which of those 2 rules I used, I'm going to use these new left and right notation. Just left is going to mean I'm going to prove A or B by proving A, and here's my proof P of A. Right is going to mean I'm going to prove A or B by proving B, and here's my proof P of B. So it's going to be my notation for introducing or terms. And by the way, some people instead use in L and in R for these, for I guess introduction left, introduction right. I think that's kind of ugly, but you'll also see that. So those are my rules for introducing or terms. And now I'm going to have rules for using or terms. Remember that we had this case analysis rule, which said if I know that A or B is true, and if A implies C and B implies C, I should be able to learn C. And so what I've done is I've named these implication rules with Fs because they're like lambda-ish things. We can think of them as functions. And then I'm just going to invent this notation cases for combining the P and the implication for A and the implication for B together. So those are going to be my my rules for introducing and eliminating or terms. So questions about new syntax for elimination and introduction rules. Okay. Well, in that case, that brings us to this final sort of big moment where everything comes together, which is, so far we've discussed proof rules. Then we set ourselves up this kind of odd problem of writing down proofs by having a concise formal language for writing down which proof rules we used in what order how. And so we did that. Now we have this whole set of syntax for writing down proof rules, for writing down formally how we use proof rules for like implication and quantification and or. And by the way, there's you can write down, I didn't cover every possible logical connective, but you can similarly do this for existentials and negation and et cetera, et cetera. So that brings us to this kind of final question, which is like, why did those proof rules look like lambdas? Why did I use lambdas and like pairs as my syntax for these individual proof rules? And that's kind of this philosophy of propositions as types, which says like, look, proofs are composed of simple proof rules, introduction, elimination, and proof terms, proof descriptions that records which rule is used when. So we've got this special syntax for each introduction elimination rule. And it turns out, like, weirdly enough, that those proof rules look a lot like programs if you choose your syntax carefully. The rules for implications look a lot like function terms. The rules for and look a lot like structures or tuples. The rules for or terms look a lot like unions. So why is that? Well, this philosophy basically says it's because deep down, these are the same thing. Proofs are programs, propositions are types for those programs. Or alternatively, a proposition is kind of like the type whose values are all of the proofs of that proposition. So that kind of gives us this interesting idea that we might be able to mix the two. Like if proofs are programs and propositions are types, then it might be possible to have a single language which operates both on values, where you can write down programs, and also on proofs, where you can write down proofs about those values. It might be possible to reuse the same syntax for programs and for proofs. Like, look, if we're using lambdas to write down our proof of an implication, and we're using lambdas to write down programs that are functions, we just use the same syntax for both. And it should also be possible to, in that case, write down data structures that kind of mix the two. Because your syntax is the same, the values are presumably going to be the same as well. You can have one data structure that contains both a program or like some programmatic value and also a proof about that value. And ultimately, this kind of means in such a language, whether something is a proof of some proposition or it is a program of a certain type, it's kind of up to your own interpretation. If you take an argument X of type A, do you want to think about that as a proposition A with a proof X of it? Or do you want to think about that as a type A with a value X from that type? It's kind of up to you. The language underlying it doesn't care. And that's this philosophy that proof assistants like Lean are built upon. So let me show you a little bit of this by proving some simple logical propositions in Lean. So I've got here the same thing we were looking at last time. We've got a little Lean setup, and I'm gonna try to write down a proof in this proof assistant, and we'll talk about how this is using or not using how we can interpret this as a program and how we can interpret this as a type. So here is one very simple theorem. We'll call it T1. And that theorem says that for all propositions P, P implies P. So I've written this down as a theorem. So I said we should think about P as a proposition. And so let's go ahead and do that. I say, suppose you have some sort of P and you have some sort of proof of it, PF. How do you go ahead and prove P? Well, you actually have a proof of it right there. So that's what I've got. Theorem says just take the proof that you had of P. That's a sufficient proof of P. So let's see what Lean actually thinks T1 looks like. You see on the right-hand side here that what Lean thinks T1 actually is it is a lambda term, which takes two arguments. That first argument is, P, and that's from that for all P. And then that second argument to the lambda term is A of type P. And it's returning A. And so naturally, if we have some kind of assumption, like suppose we have A, which is a proposition, then I can say, what is T1 of A? It says T1 of A, that's a proof that A implies A. That makes sense. But we can also say, what is T1 of int? And it says that's a function from integers to integers. And in fact, we can say if we have a proof of A, we can apply T1 to A and our proof of A, and it'll return a proof of A. But we can also apply it to T1 and 3, and it'll return an integer. And in fact, if you ask, that returns the integer 3, and this returns that proof of A. So what I've done here, I've written down a simple theorem and a proof of that theorem in Lean syntax, as we saw in the demo last time. And then I've shown you how Lean can simultaneously think of that either as a theorem that applies to propositions and their proofs, or as a function that applies to types and their values. So questions about that? Go ahead, Scholar.
Was this going to be the tool for the assignment that you ended up dropping?
No, I was going to make you do something in Checker Framework. I
Oh,
wasn't
okay.
going to give you a Lean assignment just because it would have interfered with the class project. But do not be dismayed. You can always download Lean on your own time and play around with it. There's actually a pretty good Lean tutorial that you can find on Lean's website if you're interested in this and want to play around with it more. And of course, I'll be putting the code that I do in the lecture online as well on the website. Okay, so let's look at another theorem. This is a little simplistic. Let's try to prove this. Let's try to prove this theorem of what we call modus ponens, right? It's going to say for all P and Q, if P and P implies Q, then Q. So let's take our proof of P and our proof of implication, and we're going to apply the proof of implication to the proof of P. So what you've got going on here, this is a proof term. And this is a proof term that uses function application. In Lean, function application is written just with a space. You don't usually put the parentheses like this. So this is the syntax Lean uses for applying the rule of eliminating an implication. We have an implication, and here we use it, which we call elimination. And again, we can ask Lean, what does T2 look like internally? And on the right here, if you just ignore this part, which tells you that P and Q are like propositions or types, or what Lean calls a sort, And it says it's a function. It takes two arguments, one of type P, one of P to Q, and it applies one to the other, just like we wrote down. And again, we can apply this both for, we can both apply this to propositions. So we can say, I'm going to apply T2 from A to A. My proof of A is going to be this proof of A. My proof that A implies A is going to be T1 of A. That itself, that it turns out, you know, Lean can tell us that that is a proof of A, and the particular proof of A that it is, we'll talk about this notion of reducing proofs later, is proof A. And we can also apply it to integers. So if we have a function from integers to integers, and we have an integer 2, we can apply the function x plus x, and that will itself return an integer, in this case 4, by applying this function to this value. So again, we see that what we've written down here as a theorem, a proof of some logical fact, uses the same syntax that we use for applying functions, and can in fact be used both on propositions and on functions. Let me prove one more of these. This is a logical fact that we ran into way in the beginning of the course that we actually call logical resolution. Logical resolution works like this. It says if you know that A or B is true, and you know that not A or C is true, then you know that B or C is true. So this one we're going to do by analysis of cases. And I'll first do it with using this sort of pipe style, which looks a lot like a case analysis. And then we'll look, as we've done with these others, to see the actual expression that this syntax builds. So this case analysis is going to look like this. It's going to say, well, we've got arguments A, B, and C. And then we have a proof of A or B. So that proof, that proof can be a proof of A, or it could be a proof of B. So first, let's suppose it is, let's suppose this proof is a proof of B. So that's going to be or dot in R for introduction on the right. So we've got our proof of B here, and this proof B is made into a proof of A or B using this syntax in R. And in that case, we know enough that we can prove B or C. Because we have our proof of B, we just need to introduce the or with a proof of B on the left. That's good. This deals with one case, which is if our proof of A or B specifically proves B. We can do something similar if our proof of A or C over here actually proves C. So it's going to be proof of C introduced on the right. And in this case, we can prove B or C because we have a proof of C. We just introduced that on the right. And then there's one more case. So we got the case where the left-hand side is in R. We've got the case where the right-hand argument is in R. So we just got to deal with the case where both are in Ls. So we got a proof of A, and we've got a proof of not A. And in this case, this goes back to what we discussed with an elimination rule for not. Here we have a not, and we'd like to use it. And as you recall, we do that by applying it to a proof of A. And that should allow us, that allows us to prove false. And actually in Lean, once you have false, you can say false.elim. And false.elim is the syntax for given false, learning any other particular thing you might want. And so this now is a sufficient proof of our resolution theorem. And so what can we learn here? Well, you can see a couple of things. First, you can see that these in-L and in-R syntax, we can use that in pattern matching, and we can also use that in our code to introduce proof terms. And similarly for this false.elim thing. We can also see that internally Lean converts this like pipe style into some basic underlying syntax. So we can ask, show me T3. And there's a lot going on here, but here's what it looks like. It says, we use case splitting, and the particular in Lean, case splitting is called or.rec for reasons we'll discuss next time. So we say we're going to split cases, and in particular, we're gonna split cases on A. So what that means is we're gonna look at this proof of A or B and ask, is it a proof of A or a proof of B? It says, well, here's one case. Here the hypothesis is A, and I've still got all these other arguments. Oh yeah, sorry, I've got this hypothesis A, right? So now I need to prove that if A, I should be able to prove whatever my goal is, B or C. So it says, then we do a case split on the second term. And in that case split, we're going to have two cases. One of them is going to say, well, I've got a proof of A and then also a proof of not A. Here's my proof of not A. And here is false.elim applied to H1 of H. H1 being Lean's term for proof not A, and H being its room for proof A. And then here we've got this second case in our match statement. Here we've got this first case. So you can see that what's going on here really, what's actually going on is when we write these stuff with pipes is that Lean is constructing proof terms that look exactly like what we've discussed, just a slightly different choice of words. So it calls it or.rec instead of cases. It calls it false.rec. False.elim / false.rec. It calls it in-L instead of left and right. But these are the same proof terms that we've been discussing in class that Lean is writing down for writing down these proofs. So questions about this, questions about what we've done here with writing down proof terms and mixing our syntax for function application to values and constructing proofs in Lean. Questions about that? Okay, well, in that case, let's sort of sum up what we've done today. We have introduced this general idea of having a formal language in which we write down proofs. And to achieve this formal language, we developed a set of introduction and elimination rules. Those rules kind of refer to individual steps in the proof. And then for each of those rules, we developed a piece of syntax that just collects all the things you need to apply that rule in a single place, describes the rule that you applied. Then we had this idea of, we noticed basically that our syntax for each proof rule looks a lot like syntax that you can use to write down programs. So we had this idea of a language that mixes proofs and programs. You can have computations that return values, you can have computations that return proofs. And we discovered that this looks a lot like a programming language with a static type system, kind of like, Haskell or Scheme or one of these guys with a static type system. So these are languages where you assign types to programs, and we've reinterpreted this to say that we assign propositions to proofs. Given a proof, we can determine whether it proves a certain proposition. Just like given a program, we can determine whether it returns a given type. So that is what I wanted to cover today. Next, we want to move on to sort of deepen this idea, like, is there any value in looking at proofs as kind of like programs? Turns out there are. So first, we're going to look at this idea of computation, which is going to specifically look at, programs. You can apply them to values and they compute to things. Does the same idea apply to proofs? What happens if you mix programs with proofs and do computation? And specifically, we're going to look at recursion, because proving things via recursion, which we call induction, is a very common, very important method of proof. In some sense, it's the most important method of proof. So we're gonna formalize this notion of induction, and that's going to allow us to introduce proofs about things like natural numbers and their properties, or lists or trees or other common programmatic data structures. And as soon as we talk about induction and recursion, we'll need to talk about termination as well. So I'll talk about how we ensure termination in this kind of dependently typed proof world. So that's what I've got for you today. We've got, as usual, there's some course feedback, so please fill that out. And other than the course feedback, I'm confident you are all working hard on your class projects. So I hope to see more of your class projects. I hope to see progress on all your class projects. Remember, if you are having difficulties with your class project, if you feel like you're stuck or you don't know how to do something, please reach out to send an email to me and Manasij. We'll set up a time to meet with you. Lots of students have done this already, and we'll try to help get you sorted. I think it's been useful to the people who reach out. Now, obviously, I would think that, but my hope is it's useful. So that's it. Y'all are free to go, and I'll see you in 2 days to talk about how computation and recursion fit into this proof term world.
Thanks.
No problem. Calvin, question?
Yeah, so I don't want to take up class time. If you're still available, I had a question though. About so I think that I read that like the Curry-Howard type, not the Curry-Howard, the Martin Love type theory like represents false as like not A, as A implies false.
Yeah.
Or implies like contradiction. And so does this like kind of always depend on like this like proof by contradiction? Because I've like had math professors before that actually like don't even allow me to do proof by contradiction. They're like really against it because they like don't like the law of the excluded middle or something. And I don't know.
Yeah.
if it's,
Okay.
like,
So this is
necessary
a thing that comes up sort of a lot. This is a confusion that a lot of people have. So in dependently typed proof languages, you usually find that not A is represented as A implies false. And hopefully you can see that on the screen here. So I basically asked it, like, tell me what is not A. And Lean says it is A implies false. Usually in sort of a dependently typed world, you distinguish between two notions of proof by contradiction. One notion is to prove not A, assume A, prove false. The other is to prove A, assume not A, prove false. It turns out that at least in the type theory used in Lean, the first one is valid and is kind of the only way actually to prove a negation, but the second one is not valid. It is not a valid way to prove A. So this isn't a requirement. There are plenty of proof assistants that do allow this kind of rule, but that's where this like double negation elimination thing comes up, because as you might imagine, if I add two nots in front of this, so I say to prove not A, well, that's just a specific instance of this top rule, so that's fine. So usually in math, we treat not A, and A is the same thing, but in proof assistance, we, for various reasons, usually separate them.
So I remember hearing about like weakened logics that have, for example, a proof of A, but not a proof of not a proof of
Yeah, so you can,
where we don't necessarily have proofs for all things that are false if we have a proof that something's true? Or
so basically, I mean, look, we sort of introduced today this idea of, we're going to have a logic, we're going to write down a bunch of proof rules. One question you might
my
ask,
internet's bad.
yeah, it's okay. One question you might have, I'm not saying it's like the most interesting question in the world, but it's a question you might come up with, is like, what if we just ban you from using certain proof rules? And so we call those we call those non-standard logics maybe. But you can easily ask what would happen if we removed certain rules, and usually the answer is like it'd be dumb. You wouldn't be able to prove anything interesting, and so no sane person would do that. But there is this kind of funky fact that if you remove the rule of double negation elimination, there's still a lot of things you can prove, though not quite everything. So, there are people who work on this kind of idea of like, what can you prove without using the double negation elimination rule? And there's some results there. So, for example, there's this theorem called the Gödel someone theorem. And easy to remember Gödel's name, hard to remember the other guy's name, which says that even if you can't use double negation elimination, if you could prove some property P using it, you can definitely prove not P without using it, stuff like that. So anyway, point is, people study this question. You can, there's no reason you can conceive of a logic where basically certain rules you're banned from using. And for various reasons, mostly around ensuring termination, Lean and some other proof assistants tend specifically to eliminate this one. Does that answer the question?
No, I think that answered my question. Thanks for bearing with me.
Awesome. Bradley, did you have a question?
No.
Okay. Oliver, any other questions?
I'm good, thanks.
Okay, cool. Well, in that case, I think we're done. Unless Calvin, you have another question. I see that the hand is still raised.
No, thank you.
All right, great. Yeah, the thing you posted on Rosser's trick is actually about this even weirder thing called omega consistency, which I think I'll just leave to the Wikipedia article to discuss. But is another sort of property that I mean, it's true of standard logics, but you can construct like weird logics where it's not true. Anyway, okay. In that case, I will see you all in 2 days, where we'll discuss more about termination and recursion when we talk about these sort of proof rules.